Okay, so let's close out this introductory first chapter on Introduction to Climate Science with a couple of examples of what is being done with climate models right now. And since the focus is all on climate change, let's start with the example of climate change projections made with the models. What is one of the best things you can do is to look at the warming that's, let's say, happened over the 20th century, which is well documented by measurements across the globe, and not just temperature but also other changes in humidity, glacier melt, sea level rise, and so on. Then is there a way to use the models to show that that warming is due to human activities? So we have what is called detection, where you are detecting a signal of change. Let's say we looked at temperatures over Corvallis, or you can look at global mean temperatures, and you can see that it has steadily increased, especially in the last few decades. Then how can you show whether that warming is related to human activities? In the models, that's fairly easy to do, because you force the model with obviously energy coming from the sun, but also the volcanic eruptions that happen along the way, because as we saw before, volcanic eruptions put out a lot of aerosols into the atmosphere, especially stratosphere, and create a cooling of the global temperature. And you have also changes in solar activity like sunspots, which we can model very well, as we saw before. Then of course you have increases in greenhouse gases like CO2, methane, N2O, etc., CFCs, and we also have land use change, which can be prescribed. So you take a model and you let's say started in the 20th century, beginning of the 20th century, or the Industrial Revolution, and you integrate forward with all these forcings and compare with observations to make sure that the model can reproduce the observed warming, which is seen here. So these are models, several models together, being used to simulate the temperatures from the beginning of the 20th century to the end of the 20th century. And you can see models have a range, but in general the model average covers the observed changes in the global mean temperature. What can you do then to see if the human-induced greenhouse gases and land use change are responsible for the warming? You run the model again, you simulate the 20th century again, but you just take out the greenhouse gases produced by human beings, and then you see that you end up producing this blue range of simulations, which is much lower than this purplish color and the black line here, which basically says that without the human greenhouse gas forcing, we would not have seen this warming. And this holds true for North America, for Europe, for Asia, for Australia, for the global ocean, for global land, for the globe, ocean and land, and Africa as well. So this is a clear indication of the fact that the change or the warming in the recent decades, where the unforced run and forced run, so without anthropogenic greenhouse gases and with anthropogenic greenhouse gases, begin to separate out. So we can attribute part of the warming to human impacts. That's called attribution. So we have detection and attribution. Here is another changes in sea ice cover in the Arctic from 1900 according to multi-model simulations and observations shown in the red curve here. We have some estimates from various observations, including satellites, which show that there has been a decrease in the ice cover. So it's basically area of the Arctic covered by the ice. There are other parameters like ice thickness and ice area, ice extent. The terminology can be different, because if you have sea ice which has pockmarks in them like a Swiss cheese, then you just look at the outer edge of the total ice cover, or you can actually go in and compute how much actual sea ice is there in terms of area. So let's, without worrying about those things, if we look at the simulations of the models here, a large number of models participated in this. So this is the ensemble mean and ensemble mean standard deviation, so the variability around the multi-model mean. And you can see that September sea ice extent, so observations are this red curve. This is with the smoothing so that you can see the trend. So there is year-to-year variability, which is basically smoothed out when you do the 9-year running mean. If you don't know what that means, don't worry about it. But all the models are able to reproduce the range of the observations. So observations are going from this top here down to here, and the models are basically covering both ends, with the model average falling over here. And we are of course going here from simulation to projections, because we are going into 2100. This gives us confidence that the models are able to capture the sea ice cover change over the Arctic, and we can use that to project into the future to say what will happen to the Arctic ice. But projections have lots of details, as we saw before, because for the future we have to assume how greenhouse gas emissions will change, how land use will change, how energy production and related emissions will change, how population will change, and what policy measures will be taken to reduce our own impact, and so on and so forth. So we'll come back to that, and we have looked at that a little bit as well. Another example, distribution and estimate of the changes in summer temperatures over Europe in the years 2070 to 2100, the future, compared to the base period of 1961 to 1990, which is typically used as the modern day climate. So this is calculated with a regional climate model, which means the climate model is not global, but it only covers this region of interest, which means you have to provide it information at the edges. There are lots of issues, details associated with that. Why do you do regional models? Basically, that means again your grid size can become much smaller, because the computational cost of a smaller domain is much lower than the global domain. So then you can use that difference to increase the resolution and better capture even physical features like mountains and the land use change, forest versus agriculture versus urban versus abandoned land, degraded land, deserts, and so on and so forth. And you can see that the control experiment shows so here A and B are distribution of summer temperatures for 30 years in the 20th and 30 years in the end of the 21st century. C and D are temperature change and change in temperature variability between the control simulation and the scenario simulation. So future is always done with scenarios of emission and so on, which we'll come to in a minute. So you can see that the temperature change, if there was no global warming, would be this way. So you have a mean here around 16 degrees centigrade with the tail, and here you are changing the mean as well as the tail quite a bit by using these scenarios. Okay, so you can see some regions here warm tremendously in Central Europe extending, and some regions get colder here compared to the 20th century base period. So this is obviously something that people can use for decision making. There are lots of debates about whether we should care about the results from 2070 to 2100, or worry about a shorter time period like 2030 or even 2050, and what the uncertainties are when we go that far out. There are details that the scenarios themselves add a lot of the uncertainty into the future, but in the shorter period the model uncertainties are more important, and so on. So here is another example: projected allowable carbon emissions leading to stabilization of atmospheric CO2 at given stabilization levels for burn 2.5 cc EMIC Earth system model of intermediate complexity, which is from Switzerland, I think. Tom Stoker is part of this, I suspect. For different pathways leading to stabilization, assumed trajectories of CO2 concentration in the various profiles of scenarios, implied carbon emissions as projected with the burn 2.5 cc EMIC. What happens in EMICs is that the processes are simplified, focus is much more on carbon cycle, for example, and feedbacks rather than on the details of the climate itself. But let's not worry about it right now. Profiles with delayed turning point in the atmospheric CO2 increase the DSP or atmospheric CO2 overshoot, so that's OSP scenario, are compared to the standard SP profile. So standard profile, overshoot profile, and delayed turning shooting point. The 31-year running average is applied to the results, so you can see for the future these are the various trajectories assumed, and these are the emissions going further out. When do we turn around? So if we go in this and flatten out the emission to that, then we will fall off. So depending on which range of CO2 in the atmosphere is assumed, you get different turning points. Of course, these then have to be converted to warming extremes and other details if you are interested. On shorter time scales, we have, of course, things like El Nino prediction, which has become very routine and very standard now. El Nino happens in the tropical Pacific. Why do we care if it's happening out there in the ocean? Because it affects rainfall, droughts, floods, vegetation, wildfires, fisheries, and so on across the globe, what are called teleconnections. So when you perturb the circulation here and you move the heat source, remember that climatologically this is a cold region. The Pacific cold tongue is here, the warm pool is here. It rains about 5 meters per year. When El Nino happens, this convection and rainfall moves eastward, so you get floods, mudslides, fish kill, and so on, storms, cyclones on this side, and you get droughts, wildfires, dust storms, and so on this side, and you also get some teleconnections across over Africa, India, South America, and so on. So we care about those, and here is the latest forecast from the Climate Prediction Center and International Research Institute for Society and Climate at Columbia University, offering probabilistic ENSO forecasts. So we have learned now that we have to give probabilistic information, which means what? This is initialized in December of 2021 and is issuing forecasts forward into January, February, March of 22 out to July, August, September of 2022. So you can see the probability that we are in a La Nina. Of course, we are in a La Nina, so that's 100%. And then it shows into December, January, February, La Nina begins to disappear. Probability of neutral conditions returning to the Pacific are equal by March, April, May, and by April, May, June into July, August, September, the forecasts say neutral conditions may persist, but then there is increasing probability of El Nino, but it's still very low compared to the probability of normal conditions. These are used extensively by bankers, by fishermen, by weather derivatives, climate derivatives, food security, healthcare, and so on and so forth. So there are tons and tons of applications of El Nino forecasts. Of course, we are now worried a lot about the CO2 that refuses to stop increasing, and the increase is accelerating. And of course, there are also historic records of how CO2 and temperature have gone together. This is from Antarctic ice cores. So we are looking at temperature and CO2. We have talked about this before. warming phase changes can be fast and abrupt. In the past, the temperature perturbations came from orbital forcing, so CO2 responded later, so temperature leads, CO2 follows. The cooling phase slows down because of cooling global temperatures, reduced water vapor, reduced snowfall rates, reduced growth of glaciers, but you can see that sawtooth pattern play out. And in the modern period, we have increased CO2 by industrial activities, fossil fuel burning. Temperature hasn't caught up yet because it is going into the ocean, it is going into melting glaciers, it's going into evaporating water from the oceans and so on. So if this relation between temperature and carbon is true in the system, then obviously this will jump again. So applications of the models is also to be able to reproduce past variabilities like this, because we don't completely know why the change in CO2 is about 100 ppm here from an ice age to a deglacial times. Okay, so there are many hypotheses, but we don't know the exact answer. But if you have a good model which can reproduce this relation of CO2 and temperature and has a good representation of carbon cycle, then maybe it can explain where those changes come from. Okay, so there are applications, and models also have to prove themselves that they can reproduce past climates as well before we can trust them for future projections. So this is the first chapter as a very broad introduction to climate modeling. We've covered a lot of ground. There may be buzzwords that you didn't understand, but don't worry, we will now get into details of explaining many of these terms, processes, simplifications, idealizations, parameterizations, equations, and various limitations as well of the models and their applications. Okay.